Okay, today we're going to be starting a new topic on waves. This is quite a large area of study in physics, and we're going to just kind of scratch the surface really on wave theory here. And we're going to begin by really looking at how to define what a wave is, because waves behave in a very specific way, and it's important to understand what makes a wave, especially when you go on to quantum mechanics and you are introduced to ideas of wave-particle duality, and knowing that both small particles can be waves and particles, you need to know what is a wave-like behaviour. So we're going to be concentrating on interference, diffraction and refraction in this study of waves. So let's look at what a wave is. So a wave can be either longitudinal, which is this one up here, or transverse. So to get an idea of a longitudinal wave, imagine you had like a slinky, and you and your friend were holding this slinky, or a spring, and you're kind of vibrating it in this direction. And you're going to get areas of compression and areas of expansion, and the wave propagates along this direction of the wave. Longitudinal waves are sound waves. And in our study, we're not really going to concentrate too much on longitudinal waves. We're going to think more about transverse waves, which are what we more commonly think of when we think of a wave. And transverse waves are what light is, and well, basically all electromagnetic radiation. So that includes radio waves and gamma radiation. All of that is all transverse waves. So it's also important that we define some terms when studying a wave. We'll just draw a long axis, and this is our point origin. Trying to draw this neatly. Okay, so our wave here has different attributes. So we've got the peaks, and we've got high peaks and low peaks. These high peaks here are called troughs, or called crests, sorry. Think of the crest of a wave. And these low ones are called troughs. The maximum height that a wave reaches is known as its amplitude. And the period, let me rewrite that, that's very messy. Period of a wave, which we define with letter T, denote with T, is defined as the length of time a single wavelength or cycle, the cycle that the wave lasts for, the cycle so how long it takes to travel through one wavelength. And a wavelength is the distance between two, so the full cycle of the wave. So it starts here, this would be half a wavelength, and that's a full wavelength. And you can measure the wavelength from any two identical points on the wave. So this is wavelength. And we use the symbol lambda to denote wavelength, and it's typically measured in meters. We've also got the frequency, which is measured in hertz, and that's defined as the number of cycles of the wave to pass a point in a second. So say we had this point here, and you had somebody here counting each time the crest passes within a second, and that would give you the frequency. And the relationship between the period and the frequency of a wave is related by the period is equal to 1 over the frequency. So it's the period is the inverse of the frequency. Now we can use this equation by manipulating our relationship between distance and velocity and time. So by using the period t, we can redefine distance as being v over f, or we can, and then we can, this displacement which occurs, so this displacement that occurs in this time is the wavelength. It goes through this cycle, so that's the wavelength, lambda. So then we get this equation, velocity of the wave is equal to the frequency times the wavelength. And this is an important formula, and it is called the wave equation. So let's look at an example of using the wave equation. So we've got this wave, this light wave. That's all meant to be kind of same, the crests are meant to be the same width, but yeah. Art's not my strong point, even if it's just a wave. 400, so the wavelength is 475 nanometers. I'll define nanometers in a minute. So the wavelength, this is a light wave. Light waves are typically, we typically speak about nanometers when we talk about light waves. A light wave has a wavelength of 475 nanometers, and it's travelling in a vacuum. So calculate A, the frequency, and B, the period. So firstly, it's in a vacuum. So in a vacuum, the speed of light, c, move it along a bit, the speed of light is c, which is 3 times 10 to the power of 8 meters per second. The speed of light not in a vacuum is slightly less. And so the speed of light is going to is that, and we want to know the frequency. We know the wavelength lambda is 475 nanometers. Now nano is times 10 to the minus 9. So that's important to remember. because when you're doing calculations using light, you're using nanometers all the time. So nano is to the minus 9 meters. So we can use our wave equation. So velocity is frequency times lambda. The velocity is 3 times 10 to the power of 8. The frequency is what we want, and lambda is 475 times 10 to the minus 9. Rearranging that, we will get the frequency to be 6.32 times 10 to the 14 hertz. And then to find the period, we use our equation for the period is equal to 1 over the frequency. So that will be 1 over 6.32 times 10 to the 14, which is 1.58 times 10 to the minus 15 seconds. Now, I said at the beginning we need to learn how to define what a wave is. So what are the properties of a wave? So all waves have in common, regardless if they're sound waves or water waves or light waves, they all reflect, they all refract, they all diffract, and they all interfere. And we're going to go through all these different properties individually and go into more detail, but this is really important to remember that these four properties are what define a wave as being a wave. If you have something that reflects, refracts, diffracts and interferes, it is a wave. And if you can show something is doing those things, you can thus prove it to be a wave. So we're going to talk about reflection first. Reflection is something that we see all the time in everyday life. You look in a mirror, you're seeing reflection. So if you've got, call this is going to be our mirror here, and what we do is when we're thinking about reflection, we draw a normal line, an imaginary normal line, perpendicular to our surface. And so we have a light wave coming in here. We call this angle theta here. This is the angle of incidence. And so the angle of incidence is the angle at which the light wave will come in and hit our mirror or our reflective surface. And then it will bounce off at this other angle here, and this is the angle of reflection. And it's important to know and to understand that the angle of incidence is always equal to the angle of reflection. And this is a law in waves and is true regardless of the type of wave and what it is reflecting off of. Now, we have a curved mirror, or this could be a radio telescope, for example, and say we've got a wave coming in from here. Now, as I said, you've got this imaginary line to the normal. The normal is going to be here, coming at that part, and so we're going to have this wave bouncing off here like that. We might have made it too large. Similarly, if you had a wave coming in here, you've got another normal coming out here, Oops, I've not done that. I've not drawn that one well at all. Let me just correct that. There we go. So these waves are coming in. They're coming in parallel, but we've got this curved surface, and so each angle of incidence here is going to be slightly different. So we have one coming in here. We have our normal, and then it's going to normal. I'm not drawing the normal nicely at all. It's almost coming in at right angles. There we go. What we then find is, because it's a curved surface, all these lines, if they're coming in parallel, they're all going to bounce off and meet at some focus. So we call this here the focus. And this is used in satellite dishes. It's used for radio telescopes, where you can get you can collect a lot of radiation, reflect it back to one central receiver here, and that receiver will then decode the information for you, and you can read the signal. The same is true for a transmitter. You can have these transmitters, and this would be an emitter, and it will bounce. This time it's the opposite direction. It'll emit a signal, and then it'll bounce off like this. But because the important thing to note is here, though you're focusing in the central point, all these angles of incidence and reflection are still the same. Now let's look at interference. We'll come back to diffraction and refraction later. So we're going to look at interference. I'm not spelling that right at all. Of coherent waves. So, first let's define what we mean by coherent. When two waves of the same type interact, they will form some kind of interference pattern. So the waves will merge and they will interfere with each other. If you were to go to a nice calm lake or body of water and throw two stones in at exactly the same time, you would see that the ripples that they create would interfere with one another. We know that intuitively when we think of water waves, but this is true for all waves. So we need to define our term coherent, but we also need to define a term called phase. So this term phase allows us to compare the point in the cycle that the wave has reached, but it has to be measured with reference to the point of another wave, and this becomes what we call the phase difference. So let's draw. It's easier to see this thing in a diagram than actually explain it with words. So we've got our wave here. Now I'm going to draw another wave, and I'm going to get a different colour. I will So this here, so we've got a trough here, a crest here and a crest here. This is what we call the phase difference. So the phase difference is a measure how far apart in the cycle the two waves are. So if you think this wave, the black wave is further along in the cycle than this peachy coloured wave, and so they're meant to be the same. The phase differences here are meant to be the same. That's my bad drawing. So this is the phase difference between the two waves. Now, this is, when we talk about phase difference, we're talking about the phase difference between coherent waves. So a coherent wave is said to have the same frequency and the same wavelength and the same velocity. And also a constant phase difference. A constant phase difference means that the difference in the position between the successive waves remains constant. That's meant to be the same. That's my bad drawing. But they're meant to be constant and they're meant to be the same. Now, if you were to set up in a room two speakers, and you had a speaker here, meant to be a speaker, there's a speaker here and a speaker here, and they're both letting out waves. I'm going to just draw this one a different colour too. But these are these speakers are sending out coherent waves. You see the wave fronts are starting to interfere, and if you were to go around with a sound meter and measure the volume of the sound at different points of your room, you would get different readings because of the interference of these waves. So interference can either be, interference can be constructive or destructive, depending on where the phase difference when the waves interact with each other. So a constructive interference will give you a maximum, and destructive will give you a minima. Let's look at this. Let's draw this so it makes it more clear. So we've got wave 1, and we've got wave 2. So we've got two maximums meeting together and two minimums meeting together. So generally, constructive interference is described in terms of what these two waves are coherent. They come together at their maximum or their minimum points, and this will result in a wave of double amplitude. So they'll join together and you'll get the amplitude will be double what the first waves were, but they're still coherent, they've still got the same frequency and the same speed, etc., etc. The thing that's changed is the amplitude. So this is constructive interference. Now if we have wave 1 and wave 2, now for this is going to be the maximum of wave 1 is meeting the minimum of wave 2, and the maximum of wave 2 is meeting the minimum of wave 1. These are going to cancel each other out. This is destructive interference. This happens at the point where the path difference of the two waves is half a wavelength. So you think this is, they're out of phase by half a wavelength, and therefore they just cancel each other out. Now, let's define what we mean by the path difference. Let's find out. Let's look at an example of a constructive. A minute, I'll show you this one first. So, you've got 2 points of light, and they're set. So this one here, it sends out these wavefronts, and this one here sends out these wavefronts. So points here, the blue points are when a peak meets a peak, and they're going to join together to have constructive interference. The pink ones are when you get a trough and a trough meeting. So again, you're going to get constructive interference, but you're going to have, so when you peak into peak, you're going to get a larger peak, trough and a trough, a larger trough. When you get the green, they cancel each other out, and you get destructive interference. Now, if you were to look at this experimentally, this is what it would look like. It would look something like this. You've got the wavefronts coming out. So this is a ripple tank, and you've got these two kind of balls that will be vibrating at a set frequency at the same time, so they're creating waves that are coherent, and you get this wave pattern. So here you get the destructive interference, and here you're getting the constructive wave interference with the maximums and the minimums as it radiates out. Also, these lines here are the lines of maximum displacement, and so the black here, that is the minimums, and the green lines, the light patches, are the maximums. So you've got the interference pattern shown. So let's talk about phase differences. So we defined what a phase difference is. So the phase difference, that's one, it's not showing. So a phase difference was when you have your two, if I have this over here, this is our phase difference. Two coherent waves, and they're just out of step from each other. And if the phase difference is what am I trying to write? Is an integer times the wavelength, we get constructive interference. But if it's not an integer number, so when this is half a wavelength out, you'll get destructive interference. You can also get partially interference where they're not fully meeting at a peak and a trough, and so you'll get something which is, so you've got something like that, and then it's not quite, it's kind of just off a wee bit, and the resultant wave will just be a bit smaller than, the amplitude will be a bit smaller, but it's not completely been destroyed. Let's just clear that just now. Oh no, it's not this one I want to clear, it's this one I want to clear, and here. Okay, that's not showing again because it's off the board. Right, so now we need to define something called path difference. So remember this, we're two different phases. We've just done phase difference, now we're going to talk about path difference. So the relationship between a maximum and minima. So say if we were to, we've got two light waves coming in, they're coherent, and we've got this board, and what we would see would have light patches, dark patches all along here if we were looking along this here. If this is like a board where the light's shining onto, and you'd have these different fringe patterns. Now, the relationship between where maximum and minimums occur can be worked out through the path difference. And the path difference is how much further one wavefront has travelled from another. So see in this value here, this wave here, this wave's going up, so this is one wavelength, 1, 2. So it's this wave has travelled 2 wavelengths to this point. Wave B has travelled 1, 2, 3. It's meant to be 3. I've fudged that a wee bit. This is 3 wavelengths. So the path difference here, the path difference for this one is going to be 3 lambda, take away 2 lambda, which is just lambda. That's the path difference. In this case, wavelength A is gone 1 and a half. That's meant to be a half. It's 1 1/4 actually, but let me just make that a bit better. It's not rubbing out. Oh, it's because it's something wrong. Okay, it's meant to be 1 1/2. This one has went 1, 2, 3. So in this side is path difference is 3 lambda, take away 1 1/2 lambda, which is going to be 1 1/2 lambda. When we've got an integer path difference, we get a maximum. When we get a non-integer path difference, we get a minimum. So the path difference if the path difference is n lambda, we get constructive interference. If the path difference is n plus a half lambda, we get destructive interference, where n must be a whole number. If the two waves meet and there is no path difference, then the answer is, and the path difference is 0, we get constructive interference. So just to make it clear, the path difference is the different distance that each wave has travelled to reach this point. Now we can use this to then apply it to Pythagoras or trig to do some more deeper investigations into what's happening. And that's what we're going to do now. We're going to look at some examples. So, two coherent waves are produced. They are separated by a distance as shown here. So I need to run there. This source, this is point 1, source 1. 1, 2, 3, 4, 5. Oh, it's meant to be 3. Sorry, 1, 2, 3. Let's just get rid of that. And let's check it's 3. 1, 2, 3. And source 2 down here. 1, 2, 3, 4, 5. And this is point A. Consider the wave from point A. So if you're looking at point A, and it's horizontal to point 1, firstly, how many wavelengths is the path difference at A? So, from the diagram, we count the wavelengths. Starting here, 1 wavelength, 2 wavelengths, 3 wavelengths. So we've got this, I'll write it here, 3 lambda. And here we've got 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths. So the path difference is going to be 5 lambda minus 3 lambda, which is 2 lambda. What is the path difference if the wavelength is 50 centimeters? So path difference is going to be 2 times 50 centimetres, which is 0.5 metres. So always put it into metres, which is going to be 1 metre. Because path difference is n lambda. If this was a destructive one, it would be the n plus a half one. And finally, C, use Pythagoras to calculate the distance between the sources. So, what we've got here is 0.1 and A is over there. We know they're horizontal, so that's there. 0.1 and 0.2 are also next to each other like that. So we've got a right-angled triangle, and we know this is 3 lambda, and we know this is 5 lambda, and so we need to find this distance here. So Pythagoras is a squared equals b squared plus c squared. So a squared is 5 times 0.5, that's going to be squared. B is, what does it matter which one's B? We will just say this is 3 times 0.5 squared plus c squared. So c squared is going to be that's going to be 1.5 times 0.5 is 2.5. 2.5 squared is 6.25 minus, this will be 1.5 squared, which is 2.25, which gives us, working on that, you get 4. So the distance will be the square root of 4, which is 2 meters apart. Now, as a wee point of interest, interference patterns are something that we are familiar with in everyday life. If you have bubbles, all the colours that you see in the bubble is caused by interference patterns with light waves. And similarly, it's exactly the same principle. When you see oil or petrol spilled on the ground and you get that beautiful kind of rainbow pattern, that is an interference pattern. And you can see the areas of light and dark and the different colours, and they're all interfering. And so interference patterns give us some very beautiful effects.